Hello everyone, in this video we are going to be building a 3D live implied volatility surface for the Indian options market. We can choose different indexes, different equity options and visualize their respective 3D surfaces live. We are going to be following all the best practices like filtering the right kind of options contract that we are going to be using for the surface, and then for interpolation we are going to be using SVI, which is Stochastic Volatility Inspired model, which is generally used by professional quant trading firms. So here is the live surface, guys. As you can see, it's updating in real time, and at the right we have the option to choose different expiries and visualize their respective implied volatilities across its different strikes. And then we also have an option to pause the front end update so that we can have a detailed look of how the surface looks and maybe find mispricing and arbitrage opportunities. And as we resume the updates, we can see the live updates are back. And yeah, if we want to see the IV surface for a different symbol, we just have to stop the IV surface. From the drop down, select either equity or index, and then we can select from the index Bank Nifty or NIFTY. So I'm choosing Bank Nifty, and then once I start the IV surface, and as you can see, the updates are here for Bank Nifty. So this is going to be a very exciting build, guys. I'm going to guide you step by step on how to make this. So stay tuned, guys. So here I have created a flow diagram. It will help you understand how things are working in the backend. So when the user clicks on the Start IV Surface button, it basically hits this API in the backend, and it sends the symbol, instrument type, maximum expiries that we set in the front end to the backend. And once we have those parameters, what the API does is it starts the first phase, which is the data collection phase, where we collect all the data that is needed for our volatility surface. So all the options contract that we require. So in this phase, what we do first is, so in the front end, the user will provide a human readable symbol, right? So let's say Nifty, Reliance, something like that. So with that symbol name, it searches in the Upstox API and it gets the instrument key for it. So basically Upstox in its like subsequent APIs, it accepts instrument key. It like recognizes symbol by its own, instrument key. So for Nifty, it could be like Nifty underscore some code. So something like that. So once we have that, what we do is in the second step, we call this API of Upstox, which will give all the contract information for that particular underlying symbol or instrument key. So it will get all the option contracts, and what we do from that is we get all the expiry dates, all the unique expiry dates that are present. So once we have those unique expiry dates, we run, we call this API option chain API for that symbol for a particular expiry. So let's say if we have 3 expiry, then we'll call this 3 times, and this will give us the entire option chain for that expiry, all the calls, puts. So once we have that for all the expiries, we store it, and then now in the next step, what we do is we filter out the options that we actually need for our volatility surface. So we can think of it this way, that when we train a machine learning model, we only use data from which the model can actually learn patterns from, and we try to avoid using noisy data from which the model can just learn noise and no meaningful patterns out of it. So similarly here as well, we will only use options which will give us a smooth surface, and we can make a meaning out of it. So I have applied a bunch of filters. We'll go through a few of them. So our main criteria is to avoid illiquid options whose IVs are very unstable and basically are very noisy in nature. So our first filter is this delta band filter, where if the delta, the option Greek of that particular contract is out of this range, this usually means that the option is very deep out of money or very deep in the money, usually is for the very illiquid contracts. And then we have the quote quality filter, where we check if the bid and ask prices are above zero, which means that it's actually trading in the market and not just simply there. And then we check for the expiry window. If the expiry of that option is today itself, then it usually means that the IV is going to move a lot, it's going to be very erratic, so we try to avoid that. Similarly, if the option is very far dated, it's going to expire like after 120 days, so it's probably going to be very liquid, so we remove it. And then frozen filter, okay. And then IV band, yeah, we try to keep IV within a particular range, not very erratic IVs or very outlierish kind of IVs we try to remove. And then yeah, we have this butterfly prune filter, where we check if for a particular IV, a particular option, its IV is very different from what its neighbor's IV is. So let's say we have 3 IVs, the contract in the middle, like let's say we have 3 contracts, 100, 110 and 120, and if the IV of the 110 strike contract is very different from the IV of the 100 strike and the 120th strike contract, then we ignore those, because what happens is that this can break the convexity of the model and can introduce butterfly arbitrage or something similar, so we remove those. And then yeah, this is an important one. So what we do is we only use out of money options to plot our surface. The reason is that out of money options are generally more liquid, and so what we do is on the left hand side we keep the out of money puts, and on the right hand side as we move towards right, we keep out of money calls. So there are a couple of reasons. One, as I told, that out of money options are generally more liquid, and then another reason is something called as put call parity, which basically means that for a particular strike, the in the money call is almost equal to the behavior of the out of money put. So that is put of call parity. So basically, to avoid deduplication and to keep very clean data, we use only out of money contracts. And one more reason is that out of money contracts generally don't have any intrinsic value. All the values are it's time related value, so the IV quality is better in those contracts. And then yeah, we have the safeguard, where after the filter, that particular expiry only qualifies to be in the surface if minimum 5 strikes survive. So yeah, once we have all those filtered options contract, what we do is we establish a WebSocket connection with the Upstox server, and we get the live data of all those options. Let's say 400 options were filtered out, then we get the live data, the live market price data, the live IV data for all those options. And once we have that data, we move to our next step, which is interpolation, and we do it using the SVI model, which is Stochastic Volatility Inspired model. So let's first understand like what is even like interpolation, why do we even need it. So as you might have seen that all these strikes for all the options or for any underlying asset, all these strikes are discrete in nature, meaning like we'll have strikes like 100, 110, 120, and the numbers or the number of strikes between them are missing. They are not continuous in nature. So but to plot a surface, to have a smooth surface, we need a continuous surface where, let's say, even if option with a strike 105 is not trading, we could see what the assumed IV or the best calculated IV there could have been. So yeah, that is the main goal of using the SIV model for interpolation, to get a smooth surface. So let's move to the first step. What we do first is we calculate the moneyness. So we can think of it like, so each option could have very different varying expiries, right? Some could have 1,000, no, not expiries, sorry, strikes. Some could have like in terms of thousands because their underlying asset is trading at that price. Some could have in 50 or hundreds. So what we do is we normalize those strikes. So generally long moneyness is 0 for ATM options, and as we move above 0, then it's generally for the out of money calls, the log moneyness is greater than 0 and it approaches 1, and then for out of money puts, the log moneyness goes in negative. The further from 0, the more out of money that put is. So yeah, once we have that, what we do is for each option we calculate the variance. So this is the variance formula, the square of volatility times the time. So yeah, the main goal of using variance is it prevents calendar spread, and basically it's very easy to work with as it's linear in nature, and yeah, it makes our calculations and everything very easy. That is the main purpose. Generally in quantitative finance, we do calculations in variance and then we back solve it to get the IV again. Okay, so once we have calculated the variance of each and every option contract, we move to the actual interpolation step, where we basically fit a curve using the SVI model through those variance point of individual discrete contracts. This is the SVI formula. WK here is the total variance, and all these other parameters help us adjust the curve in certain directions. Some move it upward, some downward, left, right, adjust the width, and those sort of things. So what we do essentially is, we don't know these values, right, except the k value log moneyness that we calculated, but what we know is the variance value, total variance for each contract, right? So what we do is we put, for each contract we run it in iteration for each contract. So for the first contract we know the variance value, we back solve the equation to estimate the A, B and all the 5 parameters whose values are unknown, and we try to make them such that when calculated they result in a value equal to or close to our market variance that we had, and we do it for each and every contract and each and every variance, and by that we will have a best guess of what could these 5 parameters value could be. So that is why we use this optimizer, which runs many iterations to check like which value can give the least amount of error and will give the variance value close to this. So what I'll try to do is I'll put up a simulation here so that you can better understand how the fitting is happening, but it's essentially back solving it to get a value very close to the variance value that we get from individual contracts. So it essentially fits a surface which is very close to all those points that we'll have. Okay, so yeah, once we have fit the curve, we check the relative error. If it's less than 10%, then we accept that curve. If it's not, then we do a linear interpolation, which is relatively simple. And then once we have that for all the expiries, remember we do the curve fitting for individual expiries, right? So let's say we have 3 expiries. So for the first expiry, for all the options we'll do the fitting. For the second expiry, we'll do the fitting for all the options, and then at the end we'll combine the all the curves together to form a 3D surface. Okay. So once we have the data points, we store it in Redis cache. It has the key IV surface /latest, and it stores it in every half a second, and the dashboard picks it up every 2 seconds and renders it on the front end. This front end is in Streamlit. So yeah, so this is essentially it. Now I hope you guys were able to get a gist of how things are working in the backend. I'll upload this flow diagrams link in my description so you guys can check it out. So yeah, we'll move to the next step where I'm going to go through the code and explain it to you, like what is happening there. Okay, so this is the code base, and it has essentially the Streamlit front end and the fast API backend. All the Streamlit code is written in just one file, this particular file called dashboard.py file. It has the basic Streamlit functions to create the nav bar and the sidebar and all those things. And then it calls the start IV surface API when the user clicks on the start IV surface button. So here is the endpoint. Okay, so when the user calls it, it accepts the parameters that we define initially, like the symbol that we want, the maximum number of expiries that we want, and then it creates a new thread. So we create a new thread so that all the IO tasks are handled by this thread, and other parts of the application don't have to wait for this particular part to get finished. So that is the main reason. And here we call the build surface bundle function, which basically starts our pipeline. So remember, in the flowchart I had defined the pipeline where we filter out the options that we first get the contracts, all the contracts, and then filter out the options that we actually want for the surface. So here we are doing that. We are first getting the instrument key for that symbol which Upstox accepts, and then once we have the instrument key, so it does it for indexes which are like Nifty, Bank Nifty, as well as for equity symbols. And then we get the options expiries. So these are like pretty basic functions. I'm not going to go in details. Here we are basically calling the API and then transforming the data as per our needs. So it will give you a list of all the unique expiries. Have the list of expiries. Then what we do is we pass it through an initial filter. So remember, we on the front end we have this parameter maximum expiries that we can use for our volatility surface. So yeah, this is that filter. If the limit is set to 12, then make sure that only 12 latest expiries are used. And once that is done, we call the select IV surface options, where we first, for each expiry, we call the Upstox API to get the option chains, all the option chains for that particular expiry. And once we have that, we run the filters. So remember, in the flowchart we had a bunch of filters. There were in total 11 filters that we run through to make sure that the options we use are liquid and have stable IVs. So these are those filters. We check the delta, we check the minimum open interest, the whether they have butterfly prone, they are meaning they are prone to having butterfly arbitrage. We check that. And yeah, once so for all the options that passes these filter checks, they are then okay, so we return those from here, and then we get to this stage. Okay, so this bundle variable basically contains all the option contracts that we have finalized for the IV surface. And as you can see, we ran that in the thread because it has a lot of IO operations like calling the API and all. So we don't want to block other workers, and hence we use the a separate thread. So yeah, once we have the bundle, we initialize our Redis instance, and then we set our key where we are going to store all the IV data to default values. So yeah, so this dictionary will be stored as a value of that key, and this key of the dictionary grid will store the data that the live IV surface will use. And once we have this, we then get runner. So get runner will basically get the IV surface runner instance, which is we can say a lifecycle management, or a layer on top of our streamer, so that we can manage how to start, stop, or restart the stream of the WebSocket connection that we are going to establish. And then this runner.restart will basically start. So yeah, this IV surface runner is the lifecycle management class that I was talking about. So here in the restart function, we restart the task to first of all connect to the WebSocket and then send all the subscriptions. So subscriptions will be all the instrument keys or all the options contract from which we want to get the live data of. So we first acquire the lock, and then make sure that the other tasks which were already running are cancelled, and then once that is cancelled, we mark the event as stopped, and then we create a new task to run the IV surface stream. So here, okay, so this is the function where we make the WebSocket connection and subscribe to all the option contracts that we need. So firstly, we do all the basic chores like get the access token and then get all the keys that we want to subscribe to, and we create a batch, and then here we connect to the WebSocket, and then we send all the subscriptions, whatever options we want to subscribe to, and once subscribed, we enter this while true loop which keeps running until we get the data from the live data from the WebSocket. So yeah, here we extract the IV and the LTP from the data that we get, and then this function is called, which is maybe publish. So this function is used as a limit throttle or a throttle limit, which makes sure that the calculations that are going to happen with the live data only happens every 500 milliseconds. So the data may arrive at very rapid speeds as it's live data, and we might be subscribing to like 400 to 500 options at a time. So every millisecond new data might come. So as a throttle limit, we make sure that we only pass through this function, or we only pass this phase if 500 milliseconds have passed, and once those 500 milliseconds have passed after the last calculation, we move ahead, and then we enter this build snapshot function, which will firstly transform the data into this dict format, which we are going to store in our Redis. But before storing it into the Redis, remember we are still left with the interpolation part. So that we are going to do in this function. So all the math of interpolation using of the SVI model is going to happen here. So when we enter here, in this function, what we do first is we group the rows by their respective expiries, and then we calculate the log moneyness. And so log moneyness is basically we divide the strikes between like -1 and 1, with -1 being the most out of money put and +1 being the most out of money call. So basically the instead of being discrete strike values like 100, 110, we divide it between like, we normalize it and divide it between like -1 and 1. So once we have that list, we then convert, we then check for whether those values are not infinite and those kind of checks, and then we convert our the expiry values into a fraction between 0 and 1. Again, we want to like normalize it, and once that is done, we iterate over each expiry, and then we make a variable called k observed. So this will be a numpy array which has all the log moneyness values for each strike, and then similarly we have this variance. So this will store this will be a numpy array which will store all the variance values for each of the option for a particular expiry. Okay, so these are all in-memory variables, and then we finally call the SVI fit slice, where we are going to do SVI calibration or SVI fitting. So in this function, what we do first is we convert the log moneyness into a numpy array, and then the observed variance into a numpy array, and then we check if all those values are not infinite, or the variance values are greater than 0. Once we have that, we check if the number of strikes are less than 5, then we simply skip that particular expiry, as if the number of strikes are low, then we won't be able to properly fit the SVI. Okay, so here is the objective function. So the goal of this objective function is to minimize the difference between the observed variance and the variance that we get from the SVI formula. So this is essentially what the goal of the function is, and then uh, we set, what we do here is we are setting the initial values for the optimizers. So the optimizer needs a starting value, right, from where it should start start the parameters and then move from there to make the resultant of the formula as close to the observed variance as possible. So we give it a good enough starting point, a good enough probable starting point where the surface actually might lie. So once we have defined that here, we define the bounds. So bounds is basically, so since the optimizer is kind of like a brute force thing where it'll try different parameter values to make the variance value as close to the observed variance value as possible. So we define the bounds that, okay, for the parameter A, the value should be between this, for parameter B, between this, for rho, between this. So this we have defined here, and then we finally we call this minimize function with the objective function, which we have defined here and discussed what it does with the initial parameter values. And the optimizer that we are going to use is the LBFGSB optimizer with the bounds as defined here. So once it's done minimizing the objective, it should return the parameter values which gave us the variance closest to the observed variance. And yeah, so once we have that, we extract those A, B, rho, M and sigma, all these parameters, and we return it. And once we have a particular fit curve for a particular expiry, we do some basic checks and iterate for all the expiries. And once we have the curve for all the expiries, we stack them together, and then we transform the data points into a grid structure for us to store it in Redis and later to be used by our Streamlit frontend. So yeah, once we have the values in the grid format, we return it over here, uh, and then we store it in Redis, and then the front end reads this as it gets updated in the Redis. So yeah, thank you so much, guys. That is it. That is all about the code. Let me know. I know, like, I have just came through the code, but let me know if you guys have any more questions. Comment down below. I'll for sure try to answer. Thank you so much.